All right, today we're diving into something truly wild. It's a fascinating and, let's be super clear, a purely hypothetical report. This is a thought experiment on the grandest scale imaginable. What would it actually take to completely transform Mars in just 20 years? Okay, let's get into it. So, this is the core question, the big, audacious idea at the heart of this entire thing. It's not about whether we should do it, but what it would take if we could. Think of it less as a plan and more as a test of our imagination, pushing way past what we think is possible. I mean, the sheer ambition is just staggering. And right off the bat, the report pulls us back down to earth with this quote. It makes it absolutely clear from the get-go that what we're about to explore is pure science fiction for us today. This isn't a viable blueprint. It's a way for us to really wrap our heads around the true, mind-boggling scale of what terraforming actually means. So, where on Mars would you even begin? Well, Phase 1 is all about tackling the two most fundamental problems. I mean, before you can even think about water or soil or life, you need a planet that isn't a frozen, airless rock. You have to build the foundation from scratch. This really just lays it all out, doesn't it? The challenge is enormous. We're talking about an average temperature that makes an Antarctic winter look like a beach vacation, and an atmosphere so thin, it's pretty much a vacuum. Solving these two issues is the first and maybe the biggest hurdle in this entire mega project. So how do you warm up an entire world? The hypothetical solution is something called a thermal ring. Get this, 10,000 giant mirrors in orbit, each one 20 kilometers wide, all focusing sunlight onto the planet's surface. It's engineering on a scale that we can't even really comprehend, designed to literally boil the frozen ice caps. Okay, what about the air? Well, even melting all the frozen gas on Mars isn't going to be enough. So the plan calls for an armada, a fleet of 1,200 ships to go out into the solar system, capture comets, and literally drag them back to Mars to vaporize in the atmosphere. It's like a planetary-scale delivery service. So let's imagine we've actually managed to give Mars some heat and a bit of an atmosphere. The job is far from over. See, without a magnetic field like Earth has, the sun would just blast that new air right back into space. So Phase 2 is all about making this new world last. And of course, adding some water. The proposed solution here is just brilliantly audacious. You build an artificial magnetic field. The plan describes this colossal 300-kilometer-wide generator that you'd park in a stable spot in space between Mars and the sun. Its only job? Create a magnetic shield to protect the planet. It is pure, wonderful, mind-bending science fiction. But how do you power a moon-sized electromagnet? According to this report, you'd need about 1,000 compact fusion reactors. You know, that little piece of technology we haven't actually invented yet. The energy requirements are just completely off the charts. Now that the planet is shielded, it's finally time to make it rain. This plan involves setting aside 300 of those comet deliveries just for their water ice, then using those giant orbital mirrors to melt it all. And then you deploy 50 floating, city-sized machines to manage the weather and kickstart the first Martian rivers and oceans. Okay, so we have a warm, wet, shielded planet with a thick atmosphere. Great, but you still can't breathe the air and you can't grow anything in the dirt. So Phase 3 is where we tackle the chemistry of making Mars truly habitable. We're moving from planetary engineering to planetary biochemistry. This chart really puts it all into perspective, doesn't it? Just look at that tiny little sliver of oxygen on Mars today versus the goal. If we just planted trees, it would take millions of years. So to get to a breathable 20% oxygen in only 2 decades, you have to forget biology and turn to absolute industrial brute force. And that brute force comes in the form of 50,000 industrial plants spread all across the planet, working 24/7 for 20 years straight. Their only job, to crack water into hydrogen and oxygen and just pump that oxygen right into the air. And at the same time, you have to fix the dirt. Martian soil, or regolith, is actually toxic to Earth life. So this wild scenario calls for 10,000 biofabrication units. Think of them as giant factories that use genetically engineered bacteria to chew through the regolith and turn it into something that can actually support plants. And now, finally, the payoff. After nearly 2 decades of this monumental, planet-breaking effort, we get to Phase 4. All the hard work is done, all the groundwork is laid. It is finally time to seed the planet and bring it to life. Yeah, seeding a whole planet is no small task. We're talking about fleets of drones spreading billions of tons of specially engineered starter life, like hardy lichens and algae. But even then, this new biosphere isn't self-sustaining. You'd need a massive network of thousands of atmospheric machines and satellites just to keep the fragile new climate from completely collapsing on itself. All right, let's just take a final step back and really absorb the sheer, unbelievable scale of this whole hypothetical project. The report ends by basically giving us the shopping list, and the numbers are just, well, see for yourself. It's a reality check. First, you've got that ring of 10,000 solar mirrors, a constellation of structures, each the size of a small city, just to give the planet a bit of a fever. Then, you need an armada of 1,200 ships, a cosmic freight service hauling comets across the solar system to deliver air and water. Oh, and don't forget the 1,000 fusion reactors. Purely theoretical power plants, mind you, needed just to run that artificial magnetic shield. And to top it all off, an industrial complex of 50,000 oxygen factories that would dwarf anything we have on Earth, all just to make the air breathable. And this is the final, crucial takeaway. This quote from the source says it all, really. The energy needed for this 20-year project is more than all the energy humanity has produced in our entire history, multiplied many, many times over. By every single measure, it is completely impossible today. So why even think about it, right? Why write a report on something so impossible? Well, maybe exercises like this aren't about feasibility. Maybe they're about ambition. They force us to ask these enormous questions about technology, about energy, and about our place in the universe. It's science fiction for sure, but it's the kind of fiction that challenges us to imagine what a truly long-term, civilization-scale project could even look like. And that, I think, is a thought worth exploring.